let's start my presentation now. Okay.
Yeah, you can start now.
Good evening to my supervisor, Dr. Ni, and my examiner, Dr. Christopher. And now I would like to present my final year project on the topic coding for Littlewood-Richardson group for the Macdonald inner product. And in this presentation involves three. Okay. This presentation involves three parts: Young table, symmetry polynomial, and Littlewood-Richardson group. And I will quickly recap some definitions that have been presented during the midterm presentation and focus on the proving and coding part. And firstly, we define part N as a set of non-decreasing partition of N and define part as union of all part N. And next, this is the definition of Young diagram as said before. Here a new term is introduced. We can write lambda in this format for omega I to be equal to the number of parts of lambda when which equal I. And we have also defined conjugate before, and here I denote it as lambda tau. Yeah. And then the dominant ordering between partition is also introduced here. And the definition of Young table is introduced in this slide with also semi-standard Young table and standard table. Okay, next we have the definition of Young lattice here, and this is a visualization of Young lattice in this slide. And here I have used Python coding to compute the Young lattice for given, and I will explain it in next slide. And firstly, the main part I just include field line. And in this first line, I let user to input the level n that they want, and then I send the input to the function build Young lattice, followed by the function compute layout and draw Young lattice. And in the function build Young lattice, the function generate partition is to generate the partition of n from 1 to the input. And I use double for here to store all the partition into different level map. And then I create a graph G and add all the partition as nodes into G. And also I add an edge by using the function is cover in line 13. This function will check for any mu and lambda, whether we can get lambda from mu by adding exactly one box only. And it returns true if can, otherwise return false. And if it is true, it will add an edge between mu and lambda. And next, the function compute layout is just to fit the coordinate for every partition. It's also designed so that the output will look tidy like a triangle. Sorry. Is it? I think my lag a little bit. Is it still okay? Can you hear myself? Can you hear myself?
Yes, we can hear it. Hello.
Okay. Sorry for the internet interruption. Okay. So this putting the okay. So this just putting XY coordinates as they are fixed by the previous function and also label point. Oh no. It will return post and come to the next function. And this function just the draw Young lattice is just to compute the output in XY coordinates they are by the previous function. And we can define the set tab as a set of all semi-standard tables of shared lambda minus mu and word pi. And tab 0 need the word of the table to be a lattice permutation, so we can see that tab 0 is a subset of tab. And next, we are interested in filling monomial into the of the form a t to the power of b into a table with the order shown in this slide. And the statistic and sequence of regular tables is also useful to compute the word of the table filled with monomial. And we define the word of K table as the concatenator word W kappa, WT0, WT1 until WTK minus 1. And below is just a simple example. And on the other side, we are also interested in how the multiplication of tables work. And there are a few ways to define the product of table, which can be shown to be equivalent. And here we just give one way to define it, which is row insert by the step shown in this slide. And then the definition of multiplication of table and tabling are shown in this slide. Okay, next session is about the symmetric polynomial. And in this session, I will give the definition of 5 types of symmetric polynomial and state the theorem and proposition related, as well as the proof. And here, the basic part, homogeneous symmetric polynomial is defined and shown in the slide. And we'll set the number of degree n to be not greater than the number of variables L for our purpose. And then we define the set of all homogeneous symmetric functions, and we'll just set the ring to be rational number for our purpose. And next, we define lambda q as a vector space direct sum of lambda q superscript n for n greater or equal to 0. And it has the structure of Q algebra. And here we just simply write lambda subscript n, superscript n and lambda instead of these two. And next, the first type of symmetric polynomial, which is monomial symmetric polynomial, is defined and shown in this slide. And then we have these theorems say that the set of monomial symmetric polynomial is the basis of lambda n. And I'm going to briefly present the proof of this theorem. So firstly, for any two different partition lambda and mu, m lambda and m mu have no terms in common. So we can draw the conclusion that the sum of a lambda m lambda is equal to 0 if and only if a lambda equal to 0 for all lambdas. Which means that the set of monomial symmetric polynomial is linearly independent. And next, we let f to be a homogeneous symmetric polynomial of degree n. And clearly, if f equal to 0, f is a linear combination of m lambda. Therefore, we consider the case f is not equal to 0. And we use induction on the number of terms in f to prove it. For any homogeneous symmetric polynomial of degree n, it includes a term of a form like this. And by the symmetry property of f, all the symmetry in mesh after the action of SL should be in F. So we can group them together to get a term C and mu. So therefore, F minus C and mu is a symmetric polynomial and has fewer terms than F. So by induction, since F minus C and mu is a linear combination, so F is also as well. So we can say that the set of monomial symmetric polynomial of degree n spans lambda n. And next, the second type of symmetric polynomial is elementary symmetric polynomial, and its definition is shown in this slide. And here we define the row sum vector and column sum vector like this. And we define the 0, 1 matrix as the matrix whose entries are all 0 and 1. And matrix as a matrix whose entries are all natural numbers including 0. And then we have the proposition here. For any lambda, E lambda can be expressed as a linear combination of m mu. And the coefficient m lambda mu is equal to the number of 0, 1 matrix with row sum vector lambda prime and column sum vector alpha. Here lambda prime is just the extension of the lambda until L entries, where the D plus 1 until the L entries is 0. So here's the proof of this proposition. When we take the product of one term in each E lambda I, a monomial term will be produced. And this is actually equivalent to filling up one in the ij position of the matrix if the term in E lambda I include xj. So otherwise 0. So in this way, any term is uniquely correspond to a 0, 1 matrix. And next, notice that when choosing different terms in each E lambda I, we can produce the same monomial term. And they are represented by different metrics. And thus, the coefficient in this term is just the number of zero-one matrix with row sum vector lambda prime and column sum vector alpha. And also by symmetry properties of E lambda, we can group the term with each image together to get M mu with the coefficient M lambda mu. And the following is a short table of coefficient M lambda mu. And next, I will briefly present the coding to compute this equation for any lambda. And firstly, in second line, the user can input the lambda they want, and we use the function phase partition input to standardize the input into one format. And then consider a special case if the user input 0, we just show E0 is equal to 1. And in line 10, the function expand E is to count the number of 0, 1 matrix for every partition n and store in expansion. Then in line 12, I use the function format monomial to store the result in the desired format, and we output the result in line 15. So I'll skip the other coding part. If got any question, you can ask later in the Q&A session. And next, where's the proposition here? N lambda mu is equal to 0 unless the conjugate of lambda dominates mu. Well, M lambda conjugate of lambda is always 1. So we suppose M lambda mu is not 0, and we let A tilde to be a matrix with low sum vector lambda prime, and the ij position 1 for j from 1 to the lambda I, which is the left justification of the 1 in matrix A. So in this way, the number of 1 in the first I columns in A tilde is not less than the number in A. So when this equation, which is what we want as desired. So next, the set of elementary symmetry polynomials is the basis of lambda. So we set the matrix M like this, and this is the upper triangular matrix with 1 on main diagonal. So we can say that M is invertible. So we can express M lambda in terms of the linear combination of E mu. So therefore, it's a basis of lambda n. So besides, this remark is equivalent to this corollary, and we can write lambda equal to polynomial of E1, E2, and so on with coefficient in rational numbers. And next, the second type of symmetric polynomial is complete homogeneous symmetric polynomial, and its definition is shown in the slide. Then we have the proposition here. For any lambda, H lambda can be expressed as a linear combination of M mu, and the coefficient N lambda mu is equal to the number of N matrix with low sum vector lambda prime and column sum vector alpha. So actually the proof is just similar to the one before for M lambda mu, so I will just skip the proof. And the following is a short table of coefficient N lambda mu, and I will also briefly present the coding of this equation. And we can see that this matrix has no triangularity properties. So we need to consider another way to prove that the set of complete homogeneous symmetric polynomial is the basis of lambda n. And also, if the time is not enough, just stop me and I will just skip to the last part. And okay, this coding is the coefficient of N lambda mu, and it's also similar to the coding M lambda mu. Just in line 10, this function expand H is to compute the number of N matrix instead of 0, 1 matrix. And next, we come to another way to prove this is a basis. So we can define endomorphism by extending En to Hn, and we have P E lambda equal to H lambda for all partition lambda. Since phi preserve multiplication. And then the theorem said that phi is an evolution, so phi inverse equal to phi implies that phi is invertible and hence is an automorphism of lambda. So therefore, the corollary below states that the set of complete homogeneous symmetric polynomial is the basis for lambda, and is followed by this theorem and corollary before. So Next is a power sum symmetric polynomial. Its defined is shown in this slide. And this proposition is again about the coefficient out lambda mu, but is equal to number of order partition of the set D that satisfy the equation as shown in the slide. And I'll skip the proof. And here's a short table of coefficient out lambda mu. Again, it's a we can see there is a lower triangular matrix. So the proof of corollary said that the set of power sum symmetric polynomial is the basis of for lambda n is just similar to the corollary for the elementary symmetric polynomial. So the coding is the coding for computing P lambda in terms of linear combination of mu is different with the previous coding. So in line 11, the function compute P lambda extension is to compute the number of order partition that satisfy the equation in the proposition. Then we store the partition mu in n mu in its corresponding coefficient in line 16 here. And next, this part is just short the n mu in reverse reciprocity order to have a better output, and hence the output the result in line 17. And next, with the proposition here, which shows that the matrix out lambda mu is a lower triangular matrix with non-zero diagonal entries. So it's invertible, and the corollary below stating that the set of power sum symmetric polynomial is the basis of lambda n is true by this way. And last but not least, we come to the fifth basis, show polynomial. To define it, we first consider the function that makes tableau ring to polynomial ring like the equation below. Note that this span is a homomorphism. And then we define the show polynomial as the map of sum of all semi-standard Young tableau of shared lambda minus mu. Okay, then by this definition, we can define a Koska number k lambda mu as the coefficient of lambda mu. And actually, more generally, we can define the few Koska number that satisfy the equation below. And actually, there is no single formula for the Koska number like m lambda mu, n lambda mu, and r lambda mu. So we can see that there's a short table for coefficient k lambda mu. Again, is a lower triangular matrix. So it brings convenience to prove the basis part. So the coding part is coding for the coefficient k lambda mu, k lambda minus mu and nu. So this one will be a little bit complicated. So in the line 6, users are required to include one more partition mu that is smaller than lambda. So if the user just want to compute Koska number but not a few Koska number, they can just put 0 here. And then this one in line 2, the function compute skill show polynomial will first compute all the semi-standard Young tableau of shared lambda minus mu and turn it into polynomial form by the mapping that is introduced before. And then it will group them together to form a n mu with its coefficient. And then the below part is just short the order and display the output. Okay, next. This is a proposition and corollary state that the set of show polynomial is the basis of lambda m. And I will skip the proof and present the next part, which is Littlewood-Richardson rule. In this section, a lot of proof need deeper study, so I will skip this proof and just use the theorem. Firstly, the Littlewood-Richardson rule for standard inner product is introduced here. We define a scalar product by requiring m lambda and h lambda to be dual bases. Then we have the theorem before, with a focus on the last equation. And by having this theorem, we can define the Littlewood-Richardson coefficient C subscript m nu superscript lambda as an equation shown in this slide. And thus we will have the equation below. So to determine the Littlewood-Richardson coefficient for any lambda, mu, and nu, we have the theorem here. The Littlewood-Richardson coefficient is equal to the number of semi-standard Young tableau of shared lambda minus mu and where nu, whose word is a lattice permutation. So we can see the equation here. So next, the Littlewood-Richardson rule for Macdonald inner product is introduced here. So by defining it using power sum basis and showing this slide, so we got something like this, where the Z mu is equal to 1 omega 1 for omega 1 factorization here. And also we define the dual multiplication operator here. And then we have another version of Littlewood-Richardson rule, which is equal to the sum of statistics of all K table of shape lambda minus mu and weight nu minus kappa, such that the concatenated word is a lattice permutation. So we come to our main task, that is compute all K table of shape lambda minus mu and weight nu minus kappa, such that the concatenated word is a lattice permutation. And here's the coding. In the main part, user can include lambda, mu, nu, kappa, and k11. Then the main function is in line 9, the function compute tab 0k. So I will explain the details inside this function. Okay. Firstly, in line 2, I use the function table shape to compute the skew shape and store the number of boxes that can be filled out in n boxes. And next, in line 6 to 8, I just let the length of nu and kappa to be equal so that I can compute nu minus kappa easily. And then in line 11 to 15, I just compute the content of nu minus kappa. Okay, then I let t to be sufficiently large number by depending on the content of nu minus kappa. And in line 5 until 8, I store the list of constant and exponent of the monomial into base 2. And in line 11, I consider all the combination of base 2, choose n boxes element. Then I check whether the coefficient is equal to the number of content of nu minus kappa or not. If it's not, we will skip this consideration. And next, in the remaining consideration, I consider again all the permutation of them in line 2. And I start fill out the entries inside the table by using the function place into shape. Okay, after that, in line 7, if the filling that is not semi-standard yarn table, it will be skipped. So the function is semi-standard is to check the table is semi-standard or not. If it is semi-standard, it will return true. If not, it's return false. And we start to compute the concatenated word by compute the content of kappa first. And then in this line, the word is add up such that it's a concatenated word we want. And we skip the word that is not a lattice word in line 4 and 5. And now the consideration that have not been skipped is the element that we want. And we return the shorter result according to the power of statistic of table, and we compute it in the main part. And this one is the reference, and I finish my presentation. Okay, thank you. Feel free to ask any question.
Okay, we still have 7 minutes, so any question from Chris?
Sure. Let me just ask like a high level question. So how do you know the so are the Littlewood-Richardson coefficients non-negative? Yes.
You mean this one?
Or even just the one without just the one without using the statistic, just the ordinary Littlewood-Richardson coefficients. Are they non-negative? Yeah, this one. You can use either definition that you want.
This non-negative because by this theorem, it's just count the number of the semi-standard yarn table, so it should not be negative.
Yeah, that's correct. Yes. Okay. Yeah, and your code is mainly in Python.
Yeah, yes, all is in Python.
Okay, so Python also has like built-in functions for dealing with permutations and lattices and things like that. Lattice words. Okay, good. Yeah. Yeah, don't have any other questions. So those are my questions.
Okay, if not, so I got a request for Timpo. Can you, before you graduate, write a README document so that people can use this thing later?
Sorry.
Can you write a README document so that others people, when they review these things, they know how to use the code? Write
Okay.
instructions how to use it.
Okay.
Yeah.
Honestly, I think your code is quite well documented as well. Your comments looked very helpful. So that's also but yes, you of
Yeah.
course yeah. A README will also help.
Yeah. Okay, in that case, we'll end the presentation now.
Okay.
Thank you.